We're extremely excited to have Ludger presenting for us today. Just a couple of quick announcements. Again, as normal, before we kick off, that this presentation is being recorded and will uploaded to our YouTube channel after it's done. And you'll be able to find the symlink to it, the hyperlink to it on our website here for the seminar schedule, as well as seeing upcoming seminars we'll have in April and in May. If you haven't already, please join the mailing list. It's going strong, but we'll also send updates about the upcoming workshop, but also upcoming seminars to that as well. So join it if you can. And if you would like to speak or know someone who would like to speak, please feel free to reach out to us through our website with any suggestions that you have. So without further ado, I'll pass it along to Anthony to give rules of the road to introduce our speaker for today.
All right, thank you very much. Welcome back, everyone. Just a quick reminder is to please stay muted unless you're asking a question. And we are going to save questions till the end. So when we get there, feel free to raise your hand or jump in. And then we can have a good discussion at the end there. So today we're going to hear from Ludger Scherliess, who is a professor at Utah State University. He's done quite a lot, so this is my best 2 bullet point summary of his work. Basically, he focuses on low mid-latitude ionosphere and its sort of coupled systems dynamics, and does that using physics-based Kalman filter data assimilation modeling. So today we'll hear about his work on data assimilation for the ionosphere. So thanks again for joining us today, Ludger, and looking forward to hearing your talk.
Well, okay. Well, thank you very much for inviting me to do this. Let me just share my screen. Let's see, this goes well. Small. Well,
the grid is actually a really good idea. I've never seen that before. So,
wait, what is it?
The grid is actually a good idea. I've never seen that before. I need to use that.
Oh, okay.
Right. Sorry, slides look good. Take it away.
Well, okay. Well, good morning, or where you are, around the world, good afternoon, or everyone. And so I'm Ludger Scherliess, and I'm at Utah State University. And I'd like to tell you a little bit about data assimilation for the ionosphere. And so here's my outline, what I'm going to talk about today. That is, first, as I understand this is a very diverse community, the GeoDAWG community, with solar people, magnetosphere people, ionosphere people, and thermosphere, and so pretty diverse group. And so I will start with a short overview of the ionosphere, but kind of with the emphasis on what's important, what I think is important for respect to data assimilation. Talk a little about the equations that describe the ionosphere, and from there we're going to see, that where the different approaches for data assimilation come from. Talk about ionospheric data that is out there. Of course, just briefly to give you a feel of what's available. Then come to talk a little about various atmospheric data assimilation models, and with an emphasis on physics-based models for the ionosphere. So we're going to see there are others too, but that's going to be my emphasis, and I'm going to show some examples for that for different cases, and then shift focus a little bit and talk about validation, especially the need for validation. And this really came out of a workshop that we had last summer in Ionosphere, where the GeoDAWG community met for a couple of days after the YAGA meeting in Berlin, and talked about various aspects for data assimilation for the geo environment, and validation was a big part of that. And I'm going to show some of the things that we talked about there. And okay, so let's start with the ionosphere. And I know most of you are familiar, of course, with the ionosphere, but maybe not everyone is. So when we talk about the ionosphere, of course, we mean the electrically charged particles, the ions and the electrons in the upper atmosphere. And what's shown here is a plot of the various ions in the ionosphere. That's basically on the on the left side here, and you see the ionosphere extends all the way from, let's say, 60 kilometers out to several thousand kilometers, where it then goes gradually into the plasma sphere. During daytime, the ionosphere starts in the ionosphere. Starts at about 100 kilometers. Oh, just a second. Starts at about 100 kilometers, and then at 200, 300, 250, 300 kilometers, we have a peak in the density. And this peak is called NMF2. That's the main density in the ionosphere. Typically occurs somewhere around 250, but it could be as high as 500 kilometers or above, depending on what the conditions are. The corresponding height with NMF2 is HMF2. So that's, like I said, somewhere around 250 to 500 kilometer altitude. And the major ion in that region is atomic oxygen. If we look in the lower part of the ionosphere, if I show you, let's say from about 100 to 200 kilometer altitude, the main ion are in fact molecular ions. In the top part, the O+ density eventually gradually decays, becomes smaller and smaller, but H+ is going to become eventually the major ion, and this is going to be the major ion then all the way as we make our way into the plasma sphere. So these are NMF2 and HMF2 are some very important parameters that characterize the ionosphere, as they characterize the region or the altitude region and the peak density and the density of the peak in the ionosphere. Very important for various technological systems and so forth. So very often we see this and we measure this, and we characterize the ionosphere. Another very important parameter that we often use and that we can also measure is the total electron content. And that's simply, as shown here, it's the integral as we move through the ionosphere, let's say from the ground straight up, and we count all the electrons up. Basically take the electrons of the electron, take the integral of the electron density along the way and multiply this then with 10 to the minus 16. And that's the total electron content. Now, often we also talk about TEC between, let's say, a ground station and a GPS receiver, for example, or another point in space. And that's might not be vertically up, that might be at some inclination angle, at some slant angle, and we call that then slant TC, but it's the same idea. We're just adding up all the electrons that we see along the path. A very important parameter to characterize the ionosphere. Now, of course, the ionosphere is not alone in the upper atmosphere. It's embedded in the thermosphere. The thermosphere plays a very important role on the ionosphere, as we're going to see, and that's very important for the approaches that we're going to take for data assimilation. So you see here on the right here, so this is a scale here of the density, and you see the neutrals, and the neutrals, if we look, for example, at HMF2, we see that the ions are about a factor of, factor 1,000 less than the neutral density. So the neutral density is 3 orders of magnitude more dense than the ionosphere. And that, of course, has large impacts on the dynamics and the chemistry and all of this of the ionosphere. But what's great, the ionosphere? Well, the primary source is ionization, solar EUV, and X-ray radiation. The X-ray radiation is really more in the lower part, in the D region of the ionosphere, let's say below 100 kilometers, where a lot of chemistry goes on, and it only exists during the day. But if we look in the F region and also in the E region, we find that the primary source is, in fact, solar EUV in this wavelength from about 10 to 120 nanometers. The basic mechanism how this works is very simple for the main process. There's a lot, of course, of minor ion chemistry and ionization going on, but the main process is very simple. And in the F region, so we're now in the region of HMF2 here, let's say 200 to 500 kilometer altitude. It's simply that we have atomic oxygen that was created from photodissociation of molecular oxygen that gets photoionized to create O+. And of course, it creates an electron comes out there that has some excess energy, maybe a photoelectron that can do further ionization. But this is the main process. And this is not the end necessarily of the process. O+ can undergo chemical reaction, for example, with molecular nitrogen to create NO+. It's very important in the lower part, in the E region, in the F1 region of the ionosphere, or chemically react with O2 to create O2+. Yeah, so we get O+, that's the constituent of the major constituents in the F region, and we have the moleculars there. In fact, the more important ion in the lower part in the E region. If we go into the top side, the main effect is the charge exchange between, it's a resonant charge exchange between O+ and atomic hydrogen. So O++ H exchanges charges and creates H++ O, and this can go vice versa as a resonant reaction, but that creates the H+ in the that's the major ion in the top side. So fairly simple production mechanisms here for the main ions. Now there's of course a lot of other chemistry, a lot of other minor photoionization going on for other species, but these are the main processes. Similarly, this is the production. Similarly, for the loss processes, we also just have a few, main processes that do most of the damage, do most of the loss of the ionosphere. And I already talked about this O++ molecular species in the neutral densities. O++ N2 creates NO+. O++ O2 creates O2+. But this might not be the end of the reaction. NO+ then, for example, can recombine with an electron to create N+ O. So it loses its charge, and similarly, O2+ can recombine with an electron to create two atomic oxygen atoms. These are the loss processes are there during the day. They're there during the night, but of course, during the night, they are maybe the more important things because we don't have production. And with that, the nighttime densities are about an order of magnitude less than the daytime densities in the F region. And in the E region, it's even 2 orders of magnitude less. So the ionosphere does not entirely vanish during the night, but it's quite a bit reduced, an order of magnitude. Roughly, the D region entirely vanishes during the night. So we have this production and this loss processes. We have the chemistry going on, but that's of course just part of what happens in the ionosphere. There's also a lot of dynamics that's important. So dynamics, what's important there for the most part are electric fields and are winds that pushes the ions around. But of course, the ions also see the Earth's magnetic field, so they can't just do what they want. They're bound due to the Lorentz force to the magnetic field, and that has large implications on the dynamics of the ionosphere. This is a schematic here for the low latitude ionosphere that shows one of the most important dynamical processes, in the low latitude ionosphere, where if we look at the Earth's magnetic field, right at the equator, it's horizontal, as it shows here. And if there is an electric field, that electric field can come from various sources. Could come from the magnetosphere, a penetration electric field, for example, or it could be deduced due to dynamo action with the neutrals. So no matter where it comes from, it has an effect on the ionization, as the ionization reacts as an in the way of an E cross B drift. So let's think if we have the magnetic field here horizontal at the equator, pointing here from left to right, from south to north here, South Pole to the North Pole. And if we have an eastward electric field, then what that creates is an upward E cross B drift. So as a result of an eastward electric field, the ionization moves upward, E cross B drifts upward, but then additional forces, gravity and pressure gradient forces, also act on the ionization. And as a result of this, the ionization flows up, E cross B up, drifts up, and then flows along the magnetic field to either side of the magnetic equator. And that's creating ionization crests on the north and in the south side of the magnetic equator, called the equatorial ionization anomalies, or the Appleton anomalies. So this is a very important process in the ionosphere, driven by the electric field. So if we look at the morphology of the ionosphere, we see these crests on both sides here, in this case here, of the magnetic equator. Magnetic equator is roughly at this latitude here, and you see this enhanced densities on both sides here. Now, the important thing here is, that this was created from the electric field that's behind it. As a result of this, the strength and the location and the shape of these anomalies, for example, they embed information about the electric field. So if we do later data assimilation, we could go for simply the Appleton for these equatorial anomaly, trying to reconstruct them, or we can go another step and try to infer what the electric field was that was driving this structure. And that's one of the main things. This is just an example here. We could look at examples at mid latitudes where we also see an upward motion or downward motion. Could be reduced, could be due to various forces, and we can infer them from the ionosphere. But this is a very clear example here, and we could push this, in fact, one step further here. So we talked about the electrodynamics here, but we now introduce a neutral wind on it. Now, a neutral wind, let's say we have a northward neutral wind blowing here, a meridional wind that pushes the plasma then up the field line on the in the southern hemisphere here, pushing it up and pushing it down on the northern hemisphere, and that creates asymmetries in the anomalies. This here, for example, is a schematic of this. It comes from a model run here, where we see, that on the southern side here, the ionization was lifted up, and it was lowered on the northern side, and you also see differences in the strength here. Now, if we see this in the ionosphere, this gives us an idea of what the wind system is doing. So again, if we do data assimilation later, we can look at these features or look at the morphology of the ionosphere and infer additional information out of just measuring the ion density. For example, we can get information about the electric fields, we can get information about the neutral winds, and we can get information also about the chemical processes that I talked about before. Now, and of course, all that comes together. We look at the equations that govern the ionosphere, especially at low and mid latitudes. Here, and that's the continuity equation, that's the momentum equation, and the energy equation. And what I said now was, well, we have production and loss. Production loss in the continuity equation, and very important there is that the thermosphere plays a big role in there. So if we look at changes in the density, we can infer information, for example, about production and loss processes, and with that information about the neutral density. If we look at the momentum equation, we have the electric field appearing there. I just showed you the example of the Appleton anomalies, the equatorial anomalies, and again, by looking at the dynamics and the morphology of the ionosphere, we can get information about the electric field. We also see the magnetic field in here plays a very big role, but the magnetic field is generally taken as static. We're not changing the magnetic field like people in the magnetosphere do. The static approach is a very good approach. Of course, there are currents flowing in the ionosphere and they create magnetic fields, but for modeling the general morphology, that can be is typically neglected. But then we have other terms in here. The ion neutral collision frequency that tells us again something about the neutrals, the neutral density. We have the neutral wind in here. If from the dynamics of the ionization, we can infer information about the winds. Now we have collisions in the energy equation. We have heating in the energy equation, and cooling processes, and all these relate to various external driving forces. Heating, for example, well, what comes from the sun is very important there. Or we have heating in the plasmasphere that is transported. Energy gets transported into the ionosphere, and we can use this set of equation and observations in the ionosphere to infer information about the neutrals, infer information about electric fields, and so forth. And that leads to various approaches for data assimilation. But before coming there, let me tell you a little bit about the data sources that we have for ionospheric data assimilation, and we're in fact very lucky there. We have a whole zoo of different observations, and this is mostly due to the fact that we're dealing with charged particles, and charged particles have an effect on the propagation, for example, of electromagnetic waves, and that changes the characteristics of the electromagnetic waves, the ionosphere, and we can measure that, and from there infer what the densities are along the way. So that's, for example, used for bottom side electron density profiles from ionosondes or from digisondes, where we send a radio wave up into the ionosphere and we measure what comes back, and we can infer from it what the electron density profile is. Also very important, if we have a receiver on the ground looking at a GPS satellite, for example, or the Galileo satellite, or more generally GNSS satellites, we can infer slant TC, the total electron content between the receiver and the transmitter. And a similar thing is done when we go into space and we put a receiver on a satellite, for example, the Cosmic 2 satellite. These are low Earth orbiting satellites that have GPS receivers or GNSS receivers on board, and we can get radio occultation slant total electron content. We also get electron densities along satellite tracks, for example, from the DMSP satellites, or integrated UV emissions, from where we can infer also the electron density. For example, the SUSI instruments on the DMSP satellites, Gouvion timed, or we have GOLD at geostationary. The observations there are typically 1356 angstrom observations of that relate to the electron density squared. So what you see is that we have a diverse set of observations that have diverse geometries, and they're in fact quite complementary. Let me show you, for example, if we have the GPS satellites, and really, the big boom in ionospheric observations came with the advent of the GPS system, during the last 25 years, when there were lots of GPS receivers employed over the globe. So we have receivers on the ground that look to the various GPS satellites in view, and that's important for us. What we can get from this information is, if we look at the carrier phases of the two carrier phases transmitted from by the GPS satellites, L1 and L2, if we difference them, and we find that that difference is proportional to the total electron content between the receiver and the ground. So now if we put thousands of receivers across the globe, we can create maps like these ones, and I'm sure many of you have seen this before. So this is a map of total electron content obtained from over several thousands of ground receivers looking to various GNSS satellites, and then inferring total electron content from the observations. But you still see, even with thousands of receivers, we're pretty much bound to the land masses. So it's still very sparse over the oceans. There are, of course, a few islands out there, but in general, very sparse over the oceans. And the other thing is that the total electron content data from the ground to the GPS only provides very limited height profile information. It's an integrated measure, and we only have certain viewing geometries. So getting height information about the ionosphere out of these observations becomes rather difficult. But we can augment this with radio occultations observations that provide us the third dimension. So as I said before, with radio occultation, you put a receiver on a low Earth orbiting satellite. We have the GPS satellite out here at 22,000 kilometers, so hardly moving, as the LEO moves. The LEO just takes 90 minutes, of course, going around the Earth. So as the LEO moves with its receiver on board, it gets different geometries throughout the different links throughout the ionosphere, in occulting geometry. And if we can, for example, invert these observations and get altitude profiles of the electron density out of this. Now, some of the data assimilation models now take this observation here, take the inverted electron density profile and assimilate that, or other models assimilate straight the SLAN TC values. It depends on what your model, how it is constructed. But the important thing is that this gives you complementary data to the ground-based data. First of all, it's global. You have over land masses and over the oceans, but it also gives you this third dimension. From the ground, you're looking basically in the horizontal direction, whereas this one now gives you the altitude dimension to it. So you really want to combine this data in an optimal way. And that is where data assimilation really is at its strength. So we have a significant amount of data, and we have these equations that I showed you before, where we have this linkage to the external forces acting on the ionosphere. And now out of this, of course, a whole zoo of data assimilation models emerge that go after different parameters, different data assimilation schemes with different objectives. There are data assimilation models, for example, that only go after the plasma density, typically the electron density, so the N in this equation here, and other models take advantage of this linkage of the driving forces with morphology and the dynamics of the ionosphere that I showed before. So it's maybe not a surprise that there is a whole different zoo of models that have emerged over the years. And I like to focus a little bit on the physics-based data assimilation models for the ionosphere. Also come to some others in a second. Like I said, some of these models, they are just going after the ionospheric plasma densities. They're, for example, band-limited Kalman filters or Gauss-Markov Kalman filter models that have been developed by various groups, that are only interested in the plasma density, and with that, mostly that's the electron density. But then there are other models that, in addition to going after the ionospheric plasma densities, they also go after these drivers. So again, that's going after the electric field, for example, it's going after the neutral density, or if you look at production loss, that's where the neutral composition, for example, plays a big role. So we have these different types of data assimilation models that have emerged over the years. So we have some of them specification of ionospheric plasma densities, and others also go after these unobserved parameters, electric fields, neutral winds, neutral compositions, and so forth. Now, these are generally, the case for the physics-based data assimilation model for the ionosphere. Of course, there are others than these. And for example, we have models that have been developed that go that go after the ionospheric plasma densities, but not use the physics equation that I showed about, that you start, for example, from empirical background models from the IRI, for example, IDA4D is there one of the prime examples, or that use ionospheric profile parameters. HAIM is an example there, and there are other models out there. Or models have been developed for the coupled ionosphere-thermosphere system. That's, of course, where the neutral wind then self-consistently emerges out of it, or the neutral density. Foremost there is, of course, the work that Tomoko has done over the years, or Nick Petateller using WACM-X together with DART. And so there's a whole zoo of different models that have emerged over the years. But I want to show you some examples from the physics-based data estimation models that for only use an ionosphere model. And I'd like to show you, what's behind the Gauss-Markov Kalman filter, for example, and also what's behind the ensemble Kalman filter. So let's just start with the Gauss-Markov Kalman filter. In the Gauss-Markov Kalman filter, why do we do that? The Gauss-Markov Kalman filter is an approximation to the full Kalman filter, and that's done because the full Kalman filter is simply computationally not tractable. So it's a simplified Kalman filter. So what's the simplification? Well, the simplification is that the physics that I talked about before is not embedded in the data assimilation itself, but instead, we're using a physics model. An ionospheric physics is contained in a background field that gets subtracted from the observations. So, for example, you're using an ionospheric model. We're using, for example, the ionospheric forecasting model, the IFM, and we subtract the contribution from this model out of the observation. We're just dealing with perturbations on this background field. And then the Kalman filter solves for deviations from this background field, or solves for these perturbations on the background field. Now, the real advantage that we get from this, that we don't have to have the physics embedded in the filter itself, but instead we're using a statistical process to propagate these perturbations forward in time. And that has the large advantage computationally that we're now dealing with a diagonal state transition matrix. And that makes computations much, much simpler, much, much quicker. And we could, for example, run this on just one CPU. Now, when we have a diagonal state transition matrix that uses statistical process, you still have to worry about process noise. For example, you might wonder, how do you get that? And we get that from a static database, where we have done over 1,000 global, independent, time-dependent runs of the model under different driving forces. So we kind of cover the variation in the ionosphere with this, and we use this to construct the process noise, and that's, of course, then used in the error covariances. Now, the idea behind this is that if we would not have data, in the absence of data, that the model error covariances, they should relax to the error covariance of the background model. And that's captured in these 1,000 or 1,107 global IFM runs. So it relaxes to the variability that we see in these in this multitude of runs. The backdrop of doing this is that the model does not give you any information about the driving forces. If you're interested in that, you have to use the physics in the model, and that's done. Again, we need to do an approximation if we want to do this, but this is done in our ensemble Kalman filter approach. We call that game FP. And that now incorporates the ionospheric physics in the data assimilation. And with that, we can get information not just about the ionospheric plasma densities, but we also get information, as I showed before in the equation, about the electric fields, about the neutral wind, about the neutral composition. In our case, we're using a physics-based ionosphere plasmas ionosphere plasmasphere model. So we have interhemispheric flow, for example, included in there. We have the IGRF, a magnetic field geometry behind it. You have to get as realistic as possible there. Now, how do we get the information? How do we get the driver information out of this? Well, you have to make this part of the estimation process. You know, so we are augmenting the state. We're not just have the electron density field, the three-dimensional electron density field, for example, part of the estimation process or as part of the state vector, but we augment it with the neutral density parametrization, in our case, of the neutral density. Now, since we don't have a thermosphere model here, same thing for the electric field. We include it in the state vector and the neutral winds and other forces if you want so. For example, you know, you might solve for the F10.7 centimeter flux, you know, as a proxy for the solar EUV. Yeah. And so we're augmenting the state, and with that, the driving forces become an integral part of the estimation problem. Now, the physics over time will create the covariances between the driving forces and the electron density and the electron densities, and that's then used to infer the drivers out of the ionospheric observations. I'd like to show you the example in a second, but I first show you an example. Maybe some of you have seen this before, you know, of output of the model, just to give you a feel for the dynamics that we're seeing, you know. So this is a NMF2 in the middle here, and then you see 6 panels on the right, where we have the black dots are ionosonde observations, you know, at various stations, various low and mid latitude stations, now indicated here where with these arrows where they're from, and then the green curve is the reconstruction from the model, and you see that the model, you know, has a lot of dynamics that is seen in the also seen in the observation, captures it fairly well, yeah, but actually pretty well in this case here. But you also see differences here. For example, if you look here, this one is Ascension Island in the lower right corner, and Ascension Island, there's of course not much of ground-based observations, for example, surrounding it, you know, where this is in the middle of the Atlantic, and you see that the model has some trouble here capturing the dynamics in the seen in the observations. Important here is that the ionosonde data were not assimilated. You know, this is just a true comparison with independent data. Now, let me show you another example. This is now during a storm, the St. Patrick's Day storm of 2013. So that was an CME event that occurred on March 5th, on March 17th, of course. Now, St. Patrick's Day, 2 days earlier, it was it passed the ACE satellite, you know, and had the large effect here on day 75 and day 76 of the year, so March 13th, and this shows you, yeah, a movie of the observation. And you see the large amount here of ground-based GPS observations here. They just for better visualization mapped to the vertical here, so we can compare this with total electron content that we get from the model down here, and you see, you know, that we get a pretty good agreement between the observations and the model here. Not a big surprise. We assimilated, of course, lots of GPS data into this model. Yeah, but let me show you 2 snapshots out of these. Out of this movie to show you the difference between the quiet day and the storm day. So the day 75 was a quiet day. It was March 16th, and we're looking at the same UT here. This is 2000 UT, 2000 UT. We see the observations again in the top and the model results in the bottom. And if you look here at the model results and also at the data over the American sector here, for example, you see this beautiful equatorial anomalies. You see it in the data, you see it in the model results, and you see that that is very much enhanced during the storm. You know, much enhanced here, an indication that the electrodynamics most likely changed a lot. But we also see at mid latitudes significant difference here. And I'd like to focus a little bit on the mid latitudes here. But before doing this, I'd like to show you a what we call a kilogram of the total electron content variation throughout the quiet and the storm period here. And I'd like to focus on this sector here, you know, where at 35 degree east longitude, so we're hopping on the European sector here. You know, I'd like to show you a cut, you know, at the latitude cut, you know, through the observations and through the model at this longitude, so 35 degree longitude, and we're going to show this as a function of time. Yeah, and that's on the next slide here. Yeah, so in the top panel shows you the auroral electrojet index, AE, just as an indicator where the storm happened. You know, there was also some activity on the day before here. You see, in the middle panel, you see the observations. This is from the Madrigal database. So this is ground-based observations of total electron content. So you see, you know, some data gaps in here, but you see a large variability here. You know, you see this lightening up here. For example, here at mid latitudes this is over Europe, no, or in the northern hemisphere, and then we go into Africa as we make our way down here. Now you see this lightening up here at mid latitudes, at the upper mid latitudes here in the northern hemisphere. For example, during the storm, you see in the bottom panel the corresponding model result, and you see that there's variability throughout the quiet time initially, and then throughout the storm and into the recovery. It's very well captured here by the model. But can we learn something from this? Yeah. And as I said before, we're not just getting TC, for example, out of this, but we're getting information about the drivers. Yeah. So let's focus here on this region now at 50 geographic latitude. So we're at 35 east, 50 geographic. So we're somewhere in Europe here, and I picked that because there's a lot of ground-based GNSS data there, so I can do a good comparison here. And I show you this now as a function of time. You know, again, in the top panel we have the AE index. I just and this is basically what we had looked at before. But now we look at this location, 35 east, 50 degree north, at the total electron content, TC here, and you see three curves here. You see the green curve, that's the observation from ground-based receivers. You see the variation, you know, during the storm, this large enhancement in total electron content. You also see a red curve here. That's the result from the data assimilation model. And you see a black curve here. That's a model result without data assimilation. So this is the ionospheric plasma sphere model. That's the background model behind game FP, but just run with climatological, with empirical input, you know, just driven with HWM and ANSYS and my electric field model, you know, and you see that has no chance here to capture this dynamics. Actually doesn't do that well in the recovery phase here of the storm. But this is TC. Now what I want to focus on here is that we get additional information out of this. We get information about the meridional wind, the neutral wind, for example, out of this. And we can start to understand, you know, what's driving these changes in the total electron content. For example, if we look at this period here, now this period here we had an enhanced auroral electrojet index indicating enhanced energy input into the high latitude ionosphere, and that drove a southward meridional wind. You see here the red curve, that's the output from the model. Blue curve is the 6-day average over these variation, and you see here a negative excursion of the wind system. Negative is a southward excursion. southward excursion on the northern hemisphere pushes the ionization up the field line out of the region of recombination into a region of less neutral densities, out of recombination region. And with that, we get this enhancement in TC that you see here. This is driven during these several hours here where the wind was southward, but then it lingers throughout the entire day, and it even exists throughout the nighttime. So it's this long-lived perturbation that was created in this early hours of the day. So if we take a measurement later here, we have to go back here to understand where this comes from. This is not locally created, or it's locally created, but it's not created, for example, at that time. It was created much, much earlier. And similarly, during this time here, again, we see a southward excursion. This comes from, of course, enhanced energy input in the high latitudes, driving a southward wind and equatorward wind, pushing up the ionization here again. And in this case here, we get this large enhancement, more than a factor 2 enhancement in total electron content, that then again lingers throughout the day. And then we're in the recovery phase. I just wanted to focus on this initial period here. Let me show you another period here. This is now April 2012. Again, we're assimilated ground-based observations, ground-based TC, cosmic radio occultation data here, and ionosphere data. And we're looking throughout a stormy period in April of 2012. Again, the AE index in the top panel here, showing you the strong variability that occurred in the high latitudes. Middle panel is again this cut, this time in the American sector, 290° east here. We're going from -70 to about 55 north geographic latitude here. So through the American sector, first South America, then into North America. And you see this large variability in total electron content, from one day to the next. Here we have in the main phase of the storm, here we're in the recovery, large differences. But you see that the model captures this very well. And again, we're getting more information out of this. We're getting information about the wind system. Out of it, we can learn or understand where these variations that we see in TC. Again, here we see this, for example, this bump here in TC. Well, where did that come from? Well, there was this not even a large excursion, southward excursion of the wind. Maybe a TID even that's going through here. It almost looks like that. And of maybe 20 meters per second, that caused this enhancement in TC that then, interestingly, lingered throughout the entire night. The time constant in the through the night is several hours here. And then we have similar things, later into the storm here, where we can use the model to understand what's going on. Okay, so if we look at these results, if we look at the comparison with TEC, and we see, well, we get good agreement here, and we might get the idea here that everything's good, so the model is doing well. We're basically done, and of course, to prove that you need validation, and the CCMC did a substantial amount of validation of ionospheric and ionosphere-thermosphere models. They did this as part of the CEDAR GEM challenge for systematic assessment of ionosphere-thermosphere models, and a very thorough study by Jasun Shim. And what she did was she identified data sets for validation. Then she ran the models. Mostly of them were run at the CCMC, independent of the modelers, and then compared the model results with the observations. For example, shows here observations of total electron content, different parts during the St. Patrick's Day storm of 2013, and then we see different model results here on the on the other panels. And there's no need here to look at which models we're dealing with here, but you see that there is a lot of variability, a lot of differences, in the model results that participated in this study. But what I want to point out here is, that data assimilation also was part of this study, was run at the CCMC. So independent, this was our model here, independent of us. And what we see here is that that model, in fact, outperformed all the other models. So that's kind of gives you a very good feeling about, well, maybe not a surprise, we assimilated data. So clearly, you should be better than not knowing anything about the actual observations. Yeah. So are we done? Is this all very good and all good enough? Well, it turns out, that we need a lot of validation. And so even though the models are constrained by data and data assimilation, and one might think that they should agree with reality, they don't really do. They do very, very significantly, and the data assimilation models, they display both qualitative and quantitative differences, even when assimilating the same data. And the reason for that is, there are many reasons for it, that these models use different assimilation techniques, they use different state variables, different resolutions, they have different background, or models are underlying physics, some are empirically based, different parameterizations, they use different chemical coefficients, different collision rates, and so forth. Now, different deduced external drivers, and some don't even don't do it, some do it. And so lots of variability, and all that leads to large differences in the resulting density field. And I'd like to show you an example of that. And what we did was that we looked at 4 data assimilation model results that we run independently for the same case. So we have 4 different data assimilation models. They all run the same case, and they all assimilated the same data. They all assimilated 530 ground-based GPS receivers and cosmic occultation data. And the goal was here to see the differences in the model results, and to learn from that, and also to see how different models handle the same data type. But let's focus on the differences in the model results. So here are 4 panels. If we look down here, you see we see on the left panel, it's the total electron content. Middle panel shows you NMF2. The right panel shows you HMF2. These parameters that I talked about before. And then we see 4 different models here that have different assimilation techniques, that have different physics-based models behind it, and so forth. And if we compare total electron content here, you see, well, they all agree pretty well with the from one model to the other. There are some differences in there, but they're not that significant. Well, that's maybe not a surprise. All of these models assimilated quite a bit of total electron data. But let's take a look at NMF2, and we find that in terms of NMF2, we see large differences. We see differences that are larger than a factor of 2 between the 4 model runs, especially here, for example, if we look at the equatorial anomalies for this model, we compare it with this model, we see a factor of 2 differences in there. And similarly, we find differences in HMF2, also differences that exceed 100 meters per second. So understanding this differences is, of course, very important. Where does this come from? And why do we see this? And what can we do about it? And more importantly, of course, what can we learn from this? And that, of course, needs a very orchestrated approach. And we don't really have that in place. We did this here for this run, but this is only with four models. And Of course, there are lots of reasons for this, different assimilation techniques, different models, and so forth. And I'd just like to focus a little bit on the differences in the ionospheric models, for example.
Ludger, just to jump in real quick, we have about 5 minutes left on the hour, just so you know.
Okay, perfect. Yeah, I'm getting there.
Okay,
Yep.
cool.
Thanks a lot. Yeah, so the ionospheric models, they differ by uncertain parameters. They use different chemical rates, different collision frequencies. They use different coupling formulations or incomplete or approximate coupling formulation. They have different resolutions. They have some missing physics, and there's even some simple math formulations included, for example, in the lower part of the ionosphere, and there was an entire Chapman conference dedicated to this problem for the ionospheric models, and out of that came a study that was led by Zhuwei Fang, that the equatorial PRIMO study, so problems related to ionospheric models and observations. And you see here from the list of co-authors on this study, this was basically everyone who had an ionosphere model or an ionosphere thermosphere model at the time participated in this study. And the idea was to understand, what's causing the differences in the even in if we run standalone ionosphere model or ionosphere thermosphere models. And what was done here was that the models were run for exactly the same condition, simulating condition. They all ran for March equinox, they all run for medium F10.7, and they all run for geomagnetic white time. The standalone models, so the standalone ionosphere model, all use the same empirical drivers. They used my electric field model, they used the NRL, certain version, HWM93, and the Bernstein factor, which is a fudge factor for the O+2O collision frequency, was set to 1 for all these studies. A very controlled environment. And then the observations, and then the model results were compared in the Peruvian sector, simply because there are observations in this sector for comparison. And without looking into any detail here, you get the gist here that there is a large variation, a large differences in the model results. This is so all physics-based ionosphere models. Well, there's the IRI also in there just for comparisons. But the ionosphere, but the physics-based model, even though running for the same condition, running with the same drivers, exhibit large variations. And now you use these different models for data assimilation. And of course, you get different drivers out of it. You get different results. So validation, very, very important, and understanding where this comes from. The PRIMO study, one thing, for example, that was pointed out there, is the eye-neutral collision frequency. That differs here by 30% between different models. It's the GIP model, this is SAMI2, it's not the same in SAMI3. 30% differences, large effect on the ionosphere. Just show you here, this is if you have a factor of 2 difference in the O+2O collision frequency. So a factor of 2, that's probably overdoing it. That's not the case. But you see here, we see a 30% in here. So if we have a factor of 2, we see differences. This is a percent difference here, of over 200%. And it's very complicated. It varies with local time. It varies with altitude, and so forth. So you get very different results in your ionosphere. Are coupled models the answer? Well, this was also from the study from Zhuwei. Again, the coupled models running with very controlled environment and large variations also in the coupled models, in terms of NMF2 and HMF2. So this, which brings me, that validation is very, very important. But of course has many aspects to it. Often driven by the availability of the data. It's also there are different science and user needs different validation, and that often determines what metrics is important. And one should also not forget uncertainties are not only in the models, but they're also in the observations. Yeah, and with that, I come to my last slide here. How do I think we can make progress on this? And I think that we need to devise a standardized approach here. We have to establish a list maybe of standard events that we look at, standard data sets that we can use for model validation, similarly to the Primo study that I showed you. And we select a metric, and we compare what we have, and we try to understand why we get such large differences by running even data assimilation models. So I think we have a long way to go, and I like to stop here.
Great, thank you very much. We do have one question in chat from John, and John, feel free to jump in as well if you prefer. They're asking about, in the slide comparing with Ionosphere data, you said Ionosphere data were not assimilated. What data was assimilated?
Oh, okay. In the there was in fact Ionosphere data, but from other ionospheres was assimilated. But ground-based GPS was assimilated in there. There was DMSP in situ densities at 840 kilometers were assimilated in there, and I believe there was Suzy and Suli data assimilated in that run.
Sounds good. All right, we're getting several now. So in the 4-model comparison, can you elaborate on what the differences are between the different models and how that drives the differences in results?
Yeah, so if I go back here, so that's probably refers to this slide here. Well, I have to say
Actually, I was thinking of an earlier slide where you're comparing 4 different flavors of game.
Oh, okay. So this
Yes,
one
this
here.
one.
Well, to be honest, we never we weren't really funded, to try to understand what the differences are. This was more to document that even if we run these models under very controlled situations, that what kind of differences do we see? Now, this was going towards multimodal ensemble approach. We wanted to understand, how can we build this from these models? But these models use all different data assimilation schemes. Certainly has a big impact on it. Some of them, like the Gauss Markov and the lower one, band limited, only goes after the electron density distribution, so it doesn't have information about the driving forces in there. The middle ones have information about the driving forces, but even there you see differences. So to give you an answer, I can't really tell you. It's an interplay between the data assimilation schemes and the physics-based models are different. The game full physics model, for example, includes interhemispheric flow, for example. It includes a plasma sphere. The 4D VAR model does not include a plasma sphere. It does not have interhemispheric flow self-consistently included in there. So this is kind of what I'm coming to, is that I think what's needed is a concerted effort to understand this. Unfortunately, to get something like that funded is very difficult. And I think if you would talk to Zui Fang, she would tell you all about it, how difficult it was at the time when she did the studies with the standalone ionosphere models. I think it's very important, but it's not a high priority, let's say, for funding agencies.
Go ahead.
I know there are questions, but it just what Ludger you just said, like it's a we discussed this at the workshop in the GeoDAWG workshop in July, and then we really want this Primo effort, right, to understand the last slides you had lots of things, select the events and then really come up with like how you assess and then all that, and then like, you know, what method, right? Like you're saying, and then it's unfunded, you know, mandate, well, not mandate, but need, right? And then like we should probably keep talking about it. And then I think so this is we're not gonna have solution, but thank you very much, you know, presenting this to this people who are attending this seminar. So I'd like to continue to talk about this as a sort of, you know, group, and then maybe somehow request, you know, I don't know what it takes to get the support of funding agencies, you know, at least for the maybe workshop, maybe to start with, yeah.
Yeah, right. I mean, it also has to be, you know, understood that this, with data assimilation, I think needs to be an international effort. So I think the you know, the GeoDAWG umbrella that GeoDAWG is under is probably a good approach there, or a good starting point. And
Okay.
meetings like we had in Ionosphere.
Yeah, exactly. And then we have new chair. Oh, David, you left. Oh, here you go. You heard that, right? we should figure this out. Okay, that's good. Yeah, thank you. Yeah, thank you. Yeah, it's true. It has to be international. Sorry, somebody had a question on chat. So go ahead. You have question to Ludger, right? Who was it? I cannot see everything together.
Yeah, next one was Christian.
Yeah,
Yeah, he said you need some rockets to get real measurements. I don't know if that's in relation to a specific slide, or maybe Christian can clarify if he's still here. Yeah.
Well, only rockets give you the tools, right? So it's not for a specific slide, but well, you need in situ measurements, I think. And satellites are nice, but rockets give you the real data. So you should talk with Rob to get some rockets flying.
Yeah, you're right. You know, many of the observations that we have are integrated measurements. I mean, all the TC, all the radio occultation are integrated measures. The UV measurements are integrated measurements. So yeah, in situ measurements are. We have some, you know, a little bit from DMSP, but very, very little really. And well, okay, the bottom side profiles from Ionosphere. But yeah, I agree. You know, we really don't have that much. We want to have the data sets as complementary as possible. And I think in situ plays a big role in there.
Great. Two more quick questions to finish up for the day. First is, what is the maximum altitude and gain?
Wait, can you say again?
What is the maximum altitude of the model?
All the way, it goes all the way to 30,000 kilometers, so it includes the plasmasphere.
And
you know, it varies somewhat between 20,000 and 30,000, depending on geomagnetic activity. But that's a general. Well, that's for the full physics model. Markov goes up to 1,500 kilometers.
And then last question is, how long can game predict after assimilation better than empirical models?
That is a very, of course, a very difficult question to answer. Depends a lot on the geophysical condition. You know, during a storm, if a storm hits, you're basically screwed if you can't forecast what happens to the drivers. So it really hinges on that. During quiet times, yeah, in terms of the number, I don't really want to give a number here. There was forecasting was never our primary goal. This is it's mostly specifications. But if you run the model forward, it depends a lot on you know, what the space environment is doing.
Okay, great. I think that is all we have. So thanks again, Ludger, for speaking to us today.
Well,
And,
of course, I hope it was helpful.
yeah, absolutely. And this will be posted on YouTube for everyone to revisit if they'd like as well. So
Thank you, Ludger. Very helpful to get this reminder.
Well, thanks for inviting me.
Yeah.
great. Thanks, everyone. See you next month.
Okay, bye-bye.
Thank you,
Well-
Ludger.